So in looking at the tubal sign, we have, this is evidence of the tubal sign. As you can see, there's thick walls around the cystic structure, or the ectopic. We have the ring of fire, which showing vascular flow in the wall of the ectopic, but you can also see sometimes in a corpus luteum. And then free fluid on the left, we have in the pouch of Douglas. So as you can see, posterior to the uterus, you can see free fluid. And then the Morrison's pouch, where you see free fluid between the liver and the kidney. This was actually in the first case when you see with the FAST exam. You could also see that as well, but that's where you would see the free fluid in Morrison's pouch. And that's it for this case. If anybody has any questions.
Thank you, Maddie. So Maddie, the things that we did that we could improve upon or that we could learn. So she was sent home with follow-up betas, even though there was an ectopic with a yolk sac on the ultrasound. Can you explain that?
So I think that was inappropriate management. I think because the radiology said it was probable, questionable, and some of those phrasings, I think the initially evaluating team wanted to trend the HCG, but I think that was inappropriate management. And
did they write anything in their documentation that would, I don't know, help us understand what what their confusion was? Did they say, I reviewed the films myself and this actually could be a corpus luteum, or was there anything like that?
In the attending attestation, it said, yolk sac question mark, or like questionable yolk sac, but because the patient's exam was benign, her hemoglobin was stable, her beta HCG did actually rise quite a bit over the course of 12 hours, and she had a completely benign exam. They felt the patient was stable enough to trend the HCG.
So that sounds like a mistake. But the fact that the day team caught it sounds great from a system standpoint. But other than that, were there any other misses for our team? Any other takeaways for our team? Or was this just a woman who didn't respond to methotrexate?
I think there's another takeaway. So the patient had a previous history of not following with the beta HCG after an ectopic, and one of the absolute contraindications for giving methotrexate is lack of follow-up. So I think that could have been a consideration. One thing that I did note is that this is a problem I've also run into with the ED. Sometimes it's not a problem with the ED itself, but LabCorp receiving the electronic prescription for the beta HCG. So sometimes patients have a hard time trying to get their HCG done outpatient. So the ED, we tell them to print the lab slip. Sometimes they, because they're more overwhelmed even than we are. So sometimes that can get neglected, or sometimes we would either forget to tell them. What I've personally done is to tell patients just to come back to the hospital lab to get it done. I've noticed that tends to be a lot simpler, but I think there's a systems issue in trying to get the patient the prescription, because she was trying to follow up her beta HCG this time, but also considering her history of where she was trended in the beta book for her previous ectopic and then was lost to follow up. I think that, part of like ensuring follow-up is part of the absolute contraindications to methotrexate as well.
I see that Dr. Bayat has her hand up.
Hi, good morning, Maddie. I'm sorry if I missed this, but was the pregnancy desired, and was there any documentation or counseling about whether the fact that the pregnancy was desired or not, and how that would impact their management?
It was documented the pregnancy was undesired. However, again, the patient was discharged. So it was the night team resident passed along this patient to the day team for review, just to make sure that nothing was missed. And that's when the patient was called back in. But it was an undesired pregnancy.
All right. Oh, yes,
That,
go ahead with your follow-up.
no, I was just going to say that to me, gives me even more pause, because, she not only has an ectopic pregnancy, but it's an undesired pregnancy. And absolute kudos and congratulations to the resident who made sure to pass it on to the oncoming team, because that really allowed the patient to receive the care that she needed.
Maddie, thank you for presenting two very interesting cases. But it's time for us to switch gears. So Dr. Adashi, you can go ahead and start sharing, please. And we'll just take a minute for that. Dr. Adashi, if you want, you can go ahead and unmute, and then I can help you along.
Gary, Gary is showing up as unverified in the queue over here. Is that an issue? Okay, there he is. Good.
All right, Dr. Adashi, we see your slides, which is great. Go ahead and unmute so we can hear you.
They're all set up.
All right, we hear you now. Good morning, Dr. Adashi.
You can hear me?
Yes, and everything is perfect. We can see your slide also. So I'm going to ask Dr. Sauer now to introduce you.
Before that, let's be sure we can move the slides.
All right.
How do we do that?
So on the, actually, if you just click on the middle of your slide, the slide you're sharing, you can then use the down arrow or the right arrow. So first, just click on the middle of your slide to bring your computer back to that window, and then hit the down arrow or the right arrow.
I don't think it's doing it for me.
Right? Do you have two screens or one?
I have to.
So do you have a screen called presenter view where you see your big slide and then you see a little slide, which is your next slide?
Bob, what do you think?
We are in full screen of this presentation. He's in presentation view. Ellie, your presentation that I guess is on your right screen, is that correct?
Yes.
Can you go ahead and hit the right arrow on your keyboard?
I'm sorry, say it again.
Can you go ahead and hit the right arrow that's on your keyboard?
Well, I'm moving the
Oh, it
slides.
works.
It's
There you
moving.
It's working.
It's moving.
It's working. So you're all set.
All right, there we go. All right, Dr.
Good
Sauer,
miracle.
go ahead.
Okay. Again, I apologize for my voice. I sound, I guess, like a frog or something. Always happens when you have to do an introduction to get laryngitis. It's truly a pleasure and really an honor always to introduce a lifelong academic of the stature and prominence of Dr. Ellie Adashi. These titles that we put on our announcements don't really do justice to the man. He is a tenured professor at Brown, but he's so much more than that and has lived a really remarkable life and career in women's health and in academic medicine. I first got to know Ellie around 30 or so years ago when I was serving as the program chairman of what then was the PCFS, which is now the PCRS, Pacific Coast Reproductive Society. And I'd asked him to give a distinguished lecture on ovarian physiology, as I remember. Can't remember where exactly it was, but I do remember the talk, and it was really quite impressive. And I've known him ever since. He has many, many academic accolades. If I were to list them all off, we would give him 10 minutes to talk, so I'm not going to do that. But he's held positions as a director of a fellowship, as a chief of a division, as a chair of a major department, and is the dean of a medical school. And I think that tells you an awful lot. He's a member of the National Academy of Medicine, the New York Academy of Science. I mean, I just go on and on. 20 years of continuous NIH funding, which is extremely impressive, and over 800 peer review publications. And he continues still to write, regularly, probably almost every other month or so. I see something that he'll put out. He's consulted with the federal government, with WHO, with Rockefeller, and the Bill and Melinda Gates Foundation on women's health and reproductive health. And it's because he's so well respected and so knowledgeable and so connected to people in our field, which get things done. So again, I was really pleased that he accepted the invitation, even though it's virtual, to speak to you all and for you all to get the opportunity to see what a great guy this guy is. And his topic is, I hope, is going to spark some interesting thoughts and questions. I know I've dabbled in it a bit, as he knows. And I know it brings up, dystopian world things from the old Brave New World book that we all had to read in high school. I don't know if they still read that or not, but I hope so. Written in 1932, which is amazing. So anyway, Ellie, the podium is yours. Thank you for doing this, and we'll talk later.
Thank you, Mark. I wish you a swift recovery of your vocal cords. And yes, we should probably schedule a call to catch up. I'm going to move the slides to again be sure that we are together here. Is everybody seeing the movement?
Yes.
Okay. We will talk about the future today. A future that is could be distant. It's hard to know, but it will, in due course, modify IVF, if not replace it. And in addition, might make it possible, very likely will make it possible, for same-sex partners to be the genetic parents of children, something that's obviously not feasible today. I have a separate lecture on that, and so today this will not receive much attention, but that's an important potential that I think is useful to recall. I recently wrote a commentary on the distinction between the in-person and the Zoom-mediated presentation. If you read it, you'll probably conclude that I support the in-person grand rounds, although I'm fighting a losing battle, needless to say, especially when it comes to significant out-of-state travel. This came about in the course of the COVID affair, but seems to be lasting now. I do have still a few in-person grand rounds, like at the University of Pennsylvania next week, but on the whole, we are switching to a virtual world. Shown in this slide is a photograph of the father of IVF, you could say, Bob Edwards, whose discovery we will be celebrating again in 2028, which will be about 50 years since the first IVF baby was born. You may also recall that Professor Edwards received the Nobel Prize in 2010. He was the sole individual to receive the Nobel Prize for IVF simply because his two collaborators have passed away by then. And it is the policy of the Nobel Prize Committee to award only living recipients. Sadly, Dr. Edwards himself was unwell at the time, and it was really his wife who traveled to Stockholm to receive the award on his behalf. We will speak today about the next iteration, which is known as in vitro gametogenesis, which, as I suggested, might, in time, at the very least, modify IVF, possibly replace it. It is a little difficult to pinpoint the beginning of the in vitro gametogenesis revolution, if you will, but the people who really made it happen, who, by the way, are purely and exclusively Japanese, specifically Dr. Michinori Saito, who is the last author of this paper, pointed me to this 2009 publication, although I don't think it's a very compelling example of the beginning of in vitro gametogenesis. Be that as it may, I have taken notice of this technology sometime around 2010 or so. And in 2013, when I visited Japan for a different reason, I booked a flight to Kyoto, to the University of Kyoto, and visited with Professor Saito and his close associate, who I will introduce you also to in a moment, who were virtually single-handedly making in vitro gametogenesis happen. These are the two protagonists, Professor Saito and Professor Katsuhiko Hayashi, who since then moved to Kyushu University, but at the time was working hand in hand with Professor Saito. I will mention today two paradigms, the rodent and the human paradigm, although the latter has yet to be completed. All of this really was made possible by the discovery of so-called pluripotent stem cells, be they embryonic or induced, cells that can become anything, which is a huge advance in our both scientific capabilities, but more importantly, in our clinical capabilities. You could imagine taking pluripotent stem cells and creating, let's say, amacrine neurons from them and replace those in the retina of individuals who are born without them. You can imagine the production of dopaminergic neurons, who could be injected into the striatum of patients, for example, with Parkinson's disease. And you could even imagine the development of motor neurons that, under certain circumstances, could be injected into the spinal column and result in a paralyzed individual walking again. Now, I know all of this sounds like science fiction, and it is today. But as we look into the future, I think these are at least possibilities. And the same is true for stem cell-derived gametes. Science magazine, which, as you know, has the pulse on anything science, did not lose sight of in vitro gametogenesis and dedicated a spread to it in 2021. The New England Journal of Medicine, not to be outdone, also published a paper in 2022 titled Oocytes from Stem Cells, authored by Azim Surani from Cambridge University. The National Academy of Medicine convened a workshop, which I chaired in 2023, and it is possible that a consensus committee report will follow. That workshop lasted 2.5 days and featured well in excess of 20 speakers. It's instructive to look at what the Nuffield Council on Bioethics from the United Kingdom puts on its agenda. Now, granted, this is the bioethics of anything and everything in medicine, but it's interesting to note that under human reproduction, the very first item they mention is in vitro derived gametes. This is followed by limits on maintaining embryos in culture, womb replacements, preconception screening, etc. All kinds of options, but in vitro gametogenesis leading the path. This is clearly a disruptive technology. Whether it's achievable in the human still remains to be seen. And the timeline is obviously wide open. It is good when speaking about in vitro gametogenesis to recall Brave New World, the famous book written by Aldous Huxley, which saw press in 1932, wherein he made several predictions. He suggested that eggs will be created via ex vivo ovarian cultures, that embryos will be created via in vitro fertilization, and that newborns will be born via ex vivo ectogenesis. In other words, in an artificial womb. So far, he was right on when it comes to embryos being created via in vitro fertilization, something he foresaw many years ago. The other developments, I would say, are underway. And there will be a time when perhaps the young residents in this program will attend to ectogenesis, for example, and possibly to other developments that at this point are definitely some time away. It's useful to take a look at one quote from Brave New World in chapter 1, where the so-called director of hatcheries and conditioning says, one egg, one embryo, one adult, normality. Making 96 human beings grow where only one grew before, progress. The day is not too far, and in fact, in the rodent, it's already here, that we can have in vitro derived gametes in 96 well plates. That's not true yet for the human, but it's definitely by now having been achieved in the rodent. There were conceptual obstacles to the very notion of in vitro gametogenesis by dint of the so-called soma germline barrier hypothesis, the creator of which was August Weismann, professor of zoology at the University of Freiburg, who in 1893, in his book, The Germ Cell Plasm, A Theory of Heredity, argued that the germline gives rise to the soma, which is of course correct, and is immortal by dint of that, and that the soma never gives rise to the germline, which is mortal. Well, he was right for his time, of course, but the very idea of in vitro gametogenesis is that we can take a skin cell or any other somatic cell and convert it to a gamete. And that, of course, he could not imagine, nor could we. So the idea here is relying on pluripotent stem cell technologies to engage, first of all, in somatic cell nuclear transfer, which was originally discovered in 1958 by John Garden from Cambridge University, in the UK, who published on the pages of Nature a paper on sexually mature individuals of Xenopus laevis from the transplantation of single somatic nuclei. What he did was take a somatic karyoplast, so a nucleus of a somatic cell, injected it into a enucleated oocyte, and produced what amounted to a zygote, which could then be developed into a blastocyst and feature an inner cell mass, from which one could derive embryonic stem cells. This is one starting material which we need to use if we want to get to in vitro gametogenesis. In 2006, a parallel technology was introduced by Shinya Yamanaka from Kyoto University, who published on the pages of Cell a paper titled Induction of Pluripotent Stem Cells from Mouse Embryonic and Adult Fibroblast Cultures by Defined Factors. He again took a somatic cell, injected it with a select number of transcription factors, and he produced induced pluripotent stem cells. So now we have two varieties of stem cells, two technologies that allow us to get there, both of which were recognized by a Nobel Prize in Physiology and Medicine in 2012. So back to where we are aiming today, in vitro gametogenesis is all about taking a somatic cell like a skin cell and then converting it to either an embryonic or induced pluripotent stem cells by the technologies I just described that were created by two Nobel laureates, and then guiding that pluripotent stem cell towards a gametogenic fate. Now, to do that, you have to know certain things. First of all, you have to know what cues to apply to the pluripotent stem cells so that it will move in the direction you're seeking. You need to know the sequence by which these cues are applied, the timing by which they are applied, and the niche in which they exist. By that I mean, you all know, of course, that oocytes are surrounded by granulosa cells and that their function depends on this mutual relationship. And the same is true of the sperm, which is surrounded by the Sertoli cell. Those two cell types working in unison to produce functional sperm. So here again, you need to know not just what's happening to the gamete, but also to the cells that surround it. The beginning, as you can imagine, was modest. The first paper that is often cited in this area is a science paper from 2003, which was senior authored by Hans Scholler, who was then a postdoc at the University of Pennsylvania. He is presently the director of the Max Planck Institute for Molecular Biomedicine in Germany. The type of oocytes he developed from embryonic stem cell is shown on the right lower hand portion of the slide. That same year, a Japanese investigator by the name of Toshiaki Noche also produced embryonic stem cells, took embryonic stem cells and converted them to germ cells in vitro. In 2004, George Daly, who is presently the dean of Harvard Medical School, published a paper in Nature on the derivation of embryonic germ cells and male gametes from embryonic stem cells. And that same year, René Rejo-Pera, then at UCSF, published a paper titled Spontaneous Differentiation of Germ Cells from Human Embryonic Stem Cells in Vitro. In the course of the interval between 2010 and 2020 or thereabouts, a series of papers on this subject, so press in Nature, Science, Cell. This was in the rodent, the human, the same, Nature, Cell, Embryo Journal, Cell Stem Cells, all dealing with the notion of creating germ cells from somatic cells. And so as we look at the state of the art in 2015, we can say that the germ cell specification pathway is not conserved between the rodent and the human, and that we would have to explore and investigate how this process actually is or will be operating in the lab in the context of the human. As the genetic networks involved, we discovered were also quite distinct between the rodent and the human. And so as we look at the state of the art in 2015, we can say that embryonic stem cell or induced pluripotent stem cells could be converted extragonadally to primordial germ cells. We knew that much. What we really couldn't do in 2015 is take those primordial germ cells and convert them to mature, haploid, post-meiotic gametes. In a word, we mastered the extragonadal component, but we had to yet to master the intragonadal counterpart. And so the final frontier was really developing in vitro gametes or conduct in vitro gametogenesis all the way. Take a skin cell, for example, and have a sperm or an egg emerge at the other end, depending on the source of the skin cell. Going back now to the rodent, because that's where this science has progressed so far the most, and going back to our friend Katsuhiko Hayashi, now at Kyushu University, he published a paper in Nature in 2016, which showed the reconstitution in vitro of the entire cycle of the mouse female germline. This was the first ever demonstration that you could take a skin cell, for example, and make a germ cell out of it. So he started with stem cells or induced pluripotent stem cells, converted them to primordial germ cell-like cells, combined them with gonadal somatic cells, and produced a primary oocyte, a photograph of which is shown on the lower hand side. He then proceeded to fertilize those oocytes, created blastocysts, transferred them to rodents, and created pups. In a word, he started with stem cells and ended up with pups. The same type of sequence from A to Z was accomplished on the male side by Professor Saito. The paper was titled In Vitro Reconstitution of the Whole Male Germ Cell Development from Mouse Pluripotent Stem Cells. Now, that is so far and so good the situation in the rodent, but we are not quite there in the human, and I'd like to point out how far we've gotten and how far we still have to go. Perhaps the most up-to-date state of affairs here is represented by the 2018 paper of Dr. Saito, which was published in Science and was titled Generation of Human Oogonia from Induced Pluripotent Stem Cells in Vitro. Notice that he's making it clear that he's dealing with oogonia, not with oocytes. In other words, we still got a ways to go. But what he did was what they did in the rodent, to start with human primordial germ cell-like cells, that were combined with somatic cells and then guided towards oogonia. But he could not get them to the oocyte stage, and therefore he realizes, of course, that there is more to be learned and more to be done before this process can be made clinically relevant in the human. Much of the same was accomplished on the male side by Kotaro Sasaki, who at the time and to this day was and remains at the University of Pennsylvania. So, as far as the state of human in vitro gametogenesis is concerned, we have taken it as far as the oogonia, but not as far as the M2 oocyte. And we have yet to develop a technology that will produce spermatozoa in vitro. Now, with all of that behind us, shall we say, the state of the art, we can now spend a few minutes perhaps contemplating the scientific and translational promise of this technology. First of all, this is likely to be highly contributory to the advancement of science as we know it. For one, it will provide us with an inexhaustible supply of germ cells. It will allow us to knock out one gene at a time if we so choose, and thereby study the function of those genes. This is known as functional or null mutant analysis. And it will allow us, for the first time effectively in vitro, to study germ-somatic cell interactions, which to this day, if we are honest about it, are somewhat nebulous, although we realize that they are indispensable. On the clinical side, this would, in principle, allow us to reverse germline cell failure. In other words, provide individuals who lack gametes for one reason or another, either inborn or perhaps later in life, due to one insult or another, we could in principle provide them with replacement germ cells, if you will. So we're talking about autologous gamete replacement, let's say from a skin cell source. We could also gene edit those replacements if the gametes that an individual is born with, in one way or the other, are genetically modified to a degree that is incompatible with normal conception. For example, you can think of individuals born with Turner syndrome. Could we, for example, convert those individuals into fertile counterparts? And as I mentioned, perhaps one of the most astounding breakthroughs that we may witness one fine day before too long is same-sex parenthood. And I should have said same-sex genetic parenthood, because, of course, same-sex parenthood exists today, albeit if two men are involved, then a female surrogate is clearly necessary, and so forth. And so this will be a major revision of our concepts, or the concepts we were taught when we were coming up as medical students, young physicians, etc. This is something that I would envision could happen in the course of the next decade or two, although predictions are just what they are, soft predictions, and the timelines obviously cannot be ascertained with certainty. And as I said at the beginning, IVG might also have an effect on IVF as we know it. Perhaps the most obvious modification of IVF might be the elimination of the need in stimulation with gonadotropins, which requires the women to come in to receive the injections, to be monitored prior to the surgical egg retrieval. Could we possibly bypass that by, let's say, retrieving a skin cell, converting it to an egg, and thereby avoiding the need in stimulation and the need in egg retrieval? We could potentially do away with gamete donation. Right now we have banks, as you know, which provide individuals who lack gonads or lack gametes with either eggs or sperm. That may not be necessary, again, if IVG were to become operational in a human. And to a large degree, this will convert IVF to a laboratory procedure. Now, you would still have to replace the embryo and place it in the uterus. But all the steps preceding that could, in theory, be carried out in vitro and primarily in the lab. And so IVF as we know it, anyway, is likely to be markedly revised. Yes, as I mentioned, you'll need endometrial preparation and you'll need embryo transfer. But short of that, you might be in a good position to simplify the process. Will this improve affordability and thus access? Is again an open question. As you know, IVF is costly, is not affordable by everybody, and not every state has a state mandate that makes the funding of IVF somewhat more workable. We'll have to see whether that happens with IVG. I hedge my bets here because somehow we in the good US of A have always found a way to jack up the prices no matter what the circumstances. And so whether or not this will actually transpire, of course, will be determined in the marketplace, and we will only know one way or the other by the time we get there. Now, none of this can happen in a vacuum. This is a significant modification of clinical practice, and at the very least, it will have to be approved by the FDA. In other words, it will require the FDA exercising its jurisdiction on the notion of creating eggs or sperm from a stem cell or from a skin cell or whatever source via in vitro gametogenesis, as opposed to relying on the natural process. The entity at the FDA that will almost certainly be the one responsible for assessing this technology is known as CBER, or the Center for Biologics Evaluation and Research, which is presently headed by Dr. Peter Marks, MD, PhD, who is seeing to it that the medications we use and many other processes we rely on have been carefully vetted and have been deemed to be safe. In their lingo, in vitro gametogenesis will fall under the so-called HCT/Ps, which stands for human cells, tissues, and products. Which brings us back full circle to the Nuffield Council depiction of their various priorities, with in vitro derived gametes at the very top. This reminds me to conclude with the obvious statement that this is part of the future, and that particularly the young members of the audience ought to keep an eye on this breakthrough, and because they may well be the ones applying it and using it in the various contexts that I delineated today. It's impossible to tell exactly when this will become a reality, but if I can be so bold, I would say all indications are that it's inevitable and that it's just a matter of time. So gametes to order remains to be seen. For now, stay tuned. So thank you very much for the opportunity to share this latest frontier with you. And time permitting, I'll be more than pleased to answer any questions.
Dr.
Thank you,
Adashi,
Gary.
thank you so much for that excellent review. That's it creates a lot of thoughts in my mind. Does anyone have any questions? My first question, sir, is, and I'm sorry that I'm not an expert on expressing this, but my question is that I'm worried that there might be some missing element, some missing secret sauce if you take a stem cell and turn it into a gamete, like, you know, some other component of creating a human, like mitochondrial DNA or some other cytoplasmic component or some level of methylation of DNA. Like something's missing in a pluripotent stem cell that is magically present in a gamete. Has anyone looked into this?
Well, as we know, it quote unquote works at the rodent, but you're right in saying that it works at the macro level. Has anybody looked at the fine points? I think that's happening. And as I mentioned, if it ever were to come to human use, it will have to pass the gauntlet of the FDA. And they have no other priority in mind than your well-being and mine. So, no, I think today I will be hard-pressed to recommend this technology to anybody other than as a technology in progress. But if and when this becomes a reality, you're absolutely right. We will have to carefully and meticulously ensure that this is perfectly safe. Hopefully that would have been shown or will have been shown in the rodent to be so, and then later on by the FDA. So yes, there is little question but that anything and everything in these technologies that we apply to the human, we need to be absolutely positively careful. I will point out, just by way of a historic precedent, that when you look back at the history of IVF, the body that approved it in the United Kingdom was the British Parliament. And they relied essentially on the fine skills of the investigators that introduced IVF. By the same token, although a little bit more rigorously in the United States, there have at least been hearings in front of the United States Congress before IVF came to be in the US. But here too, I'm not sure that we have achieved, if you will, the perfection that both you and I think, are striving for. But so it is. History progresses and rigorousness increases. And I suspect that IVG will be vetted far more carefully than IVF ever was.
I see that Dr. Sauer has his hand up.
Yes, thank you, Ellie, again for a great talk and a nice walk down memory lane. For the younger people in the audience, I notice, since I teach in bioethics, how often people don't even know who Robert Edwards is. And I'm kind of delighted that, even though I'm not a big fan, I watched it of Netflix, the movie Joy, that is about how he struggled to make IVF happen with Purdy and Steptoe. And the point I wanted to make was he was ostracized, as you know. He was criticized. He was marginalized and on and on. 50 years, more than 50 years ago, really for about 10 years developing IVF. And the thing I've noticed with this technology and what we were doing at Columbia with what's called three-parent IVF, or the mitochondrial replacement therapies, it struck me when we went down to the FDA to lobby for its safety and introduction, even in the research side, was the strong criticism and fear, which goes back to Huxley, about some of the issues that Dr. Ebert just brought up: downstream effects on the gene pool, lack of being natural, loss of individual autonomy because of the immortality of the germ cells that could be produced, and so forth. And how lobbyists actually came to that meeting and lined up using bioethics arguments to attack this technology, including things that you mentioned about under the advancements slide: commercialization, lack of access, unless you had money or maybe power or position, and the gene editing that would probably follow this technology. So my question, I know it's a long preface, but my question is, how do you how do you do a rebuttal to those types of arguments?
Well, it's at that point, we are really down to scientific discourse and scientific rebuttals to legitimate questions. And that's what we have the FDA for. We don't want them to sign the dotted line. We don't want them to just sit there and listen. We want them to convene the best possible people in the field, hopefully not people who have a vested interest in the technology, who would honestly, carefully, and without time constraints ask every possible question and receive any conceivable answer before they sign on the dotted line. I agree completely with what you said about Edwards and about mitochondrial replacement therapy. Still, amongst the, I think one would have to say, I think you'd agree with that amongst the novelties that are being introduced by science, reproductive novelties tend to receive the most attention. Human sensitivity when it comes to reproduction is very high. Not that heart replacement is in any way a trivial undertaking, but it's a far less loaded organ than is the ovary or the testes. And it's far less loaded function than reproductive function. So when it comes to reproduction and to the fact that that's where the perpetuation of the species transpires, etc., I would like to hope, and I believe it is the case, that the FDA looks long and hard, and the people who submit the application long before that look long and hard to make sure that whatever we are proposing is essentially, as much as we can say so, 100% facsimile of the natural process. There are no shortcuts here allowed. We cannot skip steps. The children that are born are ultimately our responsibility. And so the chain that I try to describe, leading to a final approval of this or that technology, I think needs to be highly rigorous. And that definitely was not the case when Edwards introduced IVF. Luckily for us, it has worked out, if you will. But we will be celebrating, as you know, the 50th anniversary in just a few years, in 2028. And thankfully, on the whole, this technology has brought nothing but happiness to barren couples. And my hope is that although the rigor will be hopefully much advanced, some of the same will be true for in vitro gametogenesis.
Another question for you. Interestingly, in some places in the world that have less regulation and keen interest in these technologies, and I'm really talking about China now, they could care less about all of our debates, and they seem to move these technologies forward very rapidly and with less rigorous oversight. Are you aware of any of this type of work being done in places that maybe are off the radar?
No, thank you, Mark. On in vitro gametogenesis, I would say, first of all, it's almost exclusively a Japanese undertaking. It is rather striking, surprising, almost shocking that there is very little, if any, activity in the United States. In the 2.5-day workshop that I chaired at the National Academy of Medicine, there were American speakers, but they did not, as a rule, address the biology. Now, I should say, there is a commercial outfit in Silicon Valley that is moving ahead with this idea. And so the likelihood is that we will see something commercial happening before too long. And of course, only the FDA will end up seeing the rigor of the work that may or may not have been done. But as far as open research, peer-reviewed research, published work, it's essentially exclusively Japanese in origin to this day. And it is interesting to note that compared, with other technologies. I don't really think, I haven't seen a single paper from China on in vitro gametogenesis. But as you know, you saw more than you wanted to see on germline editing. And you also saw an individual go to jail in China for that activity. He's now out of jail, but he paid the price. And so we need to give China, I think, a break on this one, in the sense that in the one reproductive technology that they did proceed with unapproved, the individual in question was tried and sentenced to prison. So having said all that, I think to you and to me, China is a closed book. I don't really think we know exactly what is or isn't going there. But I can say with confidence that I have not seen a single paper on IVG from China. It's really exclusively been a Japanese effort and effectively, exclusively the product of two universities, Kyoto University and later on Kyushu University, when one of the investigators moved from Kyoto to Kyushu. So it's a really interesting phenomenon in that respect, but it's true. These are the facts. So nothing wrong with it, but it's interesting that for one reason or another, American investigators have not taken this up in almost entirely, or definitely not in a meaningful way.
All right, well, we're just about out of time. Dr. Adashi, thank you so much for this excellent, eye-opening talk.
Thank you. My pleasure. And Mark, maybe we can arrange a phone call.
Okay. Thanks, Ellie.
All right. Will do. Thank you.
All right, thank you so much. And with that, we're
Thank
going to
you.
conclude Grand Rounds this morning. I hope everyone has a safe and successful day. Thank you.